In this video we will derive the chain rule, which is a method for differentiating a function of a function. To follow the details in this video, you'll need some familiarity with differentiation from first principles, which is covered in my video on what is differentiation. And you also need to recognize the differentials of common functions such as polynomials, trigonometric functions, exponentials, and logarithms. Have a look at my other videos if you aren't familiar with these. Consider a problem in which a function has another function embedded within it, meaning that there's more than one operation that needs to be carried out when calculating its values. In all of these cases, it's not obvious how one would go about differentiating the function. We are going to derive from first principles a method for dealing with this. Let us begin by defining a general problem of this type. Suppose we have a problem of the form h of x equals f of g of x, where f and g are known functions. For convenience, we write y equals f of u and u equals g of x. The differential of y, dy by dx, is defined as the limit, as delta x tends to 0, of h of x plus delta x minus h of x divided by delta x. Now, let's think about how h varies with x. We can plot the functions g and f separately. Thus, we have u plotted as a function of x and y plotted as a function of u. If we consider a point A on the curve in the xu plane, there will be a corresponding point in the uy plane, denoted here as A dashed. Let us suppose that A has x-coordinate capital X. Then it will have u-coordinate g of x, which I denote here with a capital U. Capital U will thus be the u-coordinate of A dashed, which in turn will have y-coordinate f of u. Now let us consider a second point B on the curve u equals g of x, a distance delta x away from A in the x direction. This will have u-coordinate g of x plus delta x, which we can also write as u plus delta u. The point B will have a corresponding point B dashed in the uy plane, a distance delta u away from A dashed in the u direction. This will have y-coordinate f of u plus delta u. We can see that the increase in u, delta u, equals g of x plus delta x minus g of x, and the increase in y, delta y, equals f of u plus delta u minus f of u. Now, we know that to find the gradient of y equals h of x, we examine the gradient of a chord in the xy plane and let delta x tend to 0. For the function of a function we have here, this takes place over both graphs. Thus, we examine the gradient of the lines passing through AB and A dashed B dashed. Before we proceed, it's worth satisfying ourselves that our method is consistent with the method of differentiation from first principles for a single function. So let's consider what happens if delta x decreases. Well, as delta x decreases, B moves closer to A. And because B stays on the curve, delta u decreases with delta x. Thus B dashed moves closer to A dashed. We can say that if delta x tends to 0, then delta u tends to 0. The gradients of the lines passing through AB and A dashed B dashed will thus change together, and on both curves we see that the gradients get closer to the gradients of the tangent at A and A dashed respectively. The gradient of y at the point x h of x is obtained by finding the limit of delta y over delta x as delta x tends to 0. Now, delta y, delta u and delta x are all finite quantities. Thus, we can write delta y over delta x as delta y over delta u times delta u over delta x. Substituting for delta y and delta u on the numerators using the expressions we have above, we get f of u plus delta u minus f of u over delta u times g of x plus delta x minus g of x over delta x. Now we let delta x tend to 0. We know that u equals g of x, thus g of x plus delta x minus g of x over delta x tends to du by dx evaluated at capital X. We also know that delta u tends to 0 as delta x tends to 0, and y equals f of u. Thus, f of u plus delta u minus f of u over delta u tends to dy by du evaluated at capital U. Thus, delta y over delta x tends to dy by du times du by dx as delta x tends to 0. In other words, dy by dx equals dy by du times du by dx. This is known as the chain rule. It can also be expressed as dy by dx equals g dashed of x times f dashed of g of x, where y is the function of a function f of g of x. Let's look at some examples. Here we have a polynomial problem y equals x squared minus 3x plus 1 to the power of 5. We could solve this by expanding the expression and differentiating each term, but using the chain rule makes it much easier to solve. If we let u equal x squared minus 3x plus 1, then we can write y equals u to the power of 5. Differentiating each of these, we have du by dx equals 2x minus 3, and dy by du equals 5u to the power of 4. Applying the chain rule, we have dy by dx equals dy by du times du by dx, which equals 5u to the 4 times 2x minus 3, and u is x squared minus 3x plus 1, thus we have 5 times 2x minus 3 times x squared minus 3x plus 1 to the power of 4. Here we have sine 3x, so we let u equals 3x and y equals sine u. Then du by dx equals 3, and dy by du equals cos u. Applying the chain rule, we have cos u times 3, which is 3 cos 3x. In example 3, we have y equals cos of x squared. Letting u be x squared and y be cos u, we have du by dx equals 2x, and dy by du equals minus sine u. Applying the chain rule, we have minus sine u times 2x, which equals minus 2x sine of x squared. In example 4, we have a different independent variable, theta instead of x, but don't let that put you off. The rule is the same. The chain rule in this case will be dy by d theta equals dy by du times du by d theta. So we let u equal tan theta and y equals e to the u. Du by d theta is sec squared theta, and dy by du is e to the u. Thus, dy by d theta is e to the u times sec squared theta, which is sec squared theta e to the tan theta. In this example, the independent variable is y, and the dependent variable is w. So the chain rule becomes dw by dy equals dw by du times du by dy. Letting u equals y squared plus 2y plus 5, we have w equals 10 to the u. Du by dy is straightforward. We have 2y plus 2. We can't differentiate w directly, so we need to think a little more carefully. Well, in this case, we have to use our knowledge of logs. Taking the natural log of u, we can see that ln w equals the ln of 10 to the u, which is equal to u times ln 10. Thus w can be written as e to the u ln 10. To differentiate w with respect to u, we need to use the chain rule again. If we write v equals u ln 10, then w can be written as e to the v. The chain rule in this case is dw by du is dw by dv times dv by du. Now, dv by du is just ln 10, which is constant, and dw by dv is e to the v. Thus, dw by du equals ln 10 times e to the v, which equals ln 10 times 10 to the u. Now we have everything we need to find dw by dy. We have ln 10 times 10 to the u times 2y plus 2. Substituting u back into our result, we have 2 ln 10 y plus 1, 10 to the power of y squared plus 2y plus 5. In example 6, we can see that the variables are phi and theta, and I do this just so that you don't always expect x and y. If we let u equals ln theta, then phi equals tan u. Du by the theta is 1 over theta, and d phi by du is sec squared u. Thus, d phi by d theta equals sec squared u times 1 over theta, which equals sec squared of ln theta over theta. This method can be used for any combination of functions, as long as we know how to differentiate each function individually. With a bit of practice, these become quite straightforward, and you can usually go straight from the original function to the differential. For example, if we have y equals cos of e to the x, we know that the differential of e to the x is e to the x, so we will be multiplying by that. It is our g dashed, or du by dx term. And the differential of cosine is minus sine. Thus we have minus e to the x times sine of e to the x. In this example, we know that the differential of x squared minus 4x plus 1 is 2x minus 4, and the differential of ln u is 1 over u. Thus, dy by dx is 2x minus 4 divided by x squared minus 4x plus 1. I recommend doing lots of examples, both using the chain rule formula and trying to do them directly as I did for the last two examples. Practice really is everything with this method.